Why shouldn't you invite mathematicians to a party? Because they can't drink and derive. Well, if you want to find out if this very bad joke makes any sense, try me tonight at the reception. But for now, I can promise that maths is so much more than derivation, integrals, or numbers, and that mathematicians aren't necessarily socially awkward elderly men. Okay, so what's on the left, it's only part of our job. Best ideas often comes in situations such as the one on the right. Maths is for the young and the old, girls and guys, smartest and average, introverts and extroverts. Maths is in everything we do. We, human beings, not necessarily mathematicians. Do you need a proof? Let me invite you to a maths party. But before we go anywhere, we have to do something about our hair. And you know, when I start preparing for a party and I look into a mirror, I assess combing my hair as an impossible task. So let's simplify this problem a bit. For a moment, forget about your head. Think about a hairy ball. Yeah, mathematicians are creative when it comes to theorem names. The hairy ball theorem is a very important result in an area of mathematics called algebraic topology that studies features of shapes. Basically, topologists care about the number of holes in objects, and they even get paid for it. Anyway, back to hairy balls. In fact, the shape doesn't really matter here, as the theorem works for any hairy creature that can be deformed into a ball without cutting, tearing, or other aggressive behaviors. So imagine you want to comb down a ball continuously covered with very fine hair, but comb it down in a way that doesn't create any tufts, nothing is sticking out, it's all smooth and flat. How can we do that? We can't. The hairy ball theorem says it's impossible. And there's one thing you should know about maths. No means no. So the theorem doesn't tell us that we just haven't found a good method of combing the hair. It says we'll never find it. It doesn't exist. Now, before you start blaming maths for tufts on your head, think about the assumptions of the theorem. Are you continuously covered with hair? If you are, then indeed maths is to blame for the bad hair day. However, most of us have hairy and less hairy parts of the body, so the theorem doesn't apply. But is it completely useless? And why on earth do mathematicians study hairy balls? Because of the Earth, indeed. It's a ball, isn't it? It's not hairy, but we have something similar here, winds. Surprisingly, they behave in a very similar way. We treat wind speeds as vectors, these little arrows that you might remember from school. And in this case, the theorem says that there is a tuft, which means there is one point on the Earth at all times where the wind isn't blowing, where the wind speed is 0. Is this theorem useless? Do I have to persuade you how useful understanding wind behavior is for weather predictions? Right. So, thanks to topology, we are ready for a party. A birthday party, in fact. And you know what? I bet 10 quid that in this room we can find at least one pair of people celebrating birthday on the same day of the year. But before you take this bet, a little spoiler. I will win with a probability of 99.99999, well, you get the idea, %. All right, but we have 365 days of the year, and it's only 150 of us in the room today. So why am I so confident I will win the bet? Let's do the maths. But before we do any calculations, a few assumptions. First, all birthdays are independent. So if we have twins in the room, could you please leave now? The same concerns people born on the 29th of February, no leap years. And finally, all dates are equally likely. So there are no peaks in birthdays 9 months after St. Valentine's Day or other events like that. All right, so you win the bet if there are no two people in the room celebrating birthday on the same day of the year. What's the probability of that? Now, maths alert, we will see some fractions. So if it might be too traumatizing, focus on the kitten. Alice and Bob are first guests to arrive to a party. Alice was born on some day of the year, so Bob has unique birthday if he was born on any of the remaining 364 days. So every next person coming into the room has 1 day less to pick from, which means that the last person, the 150th person, must have been born on any of the remaining 216 days. So to get the probability of everyone having unique birthday, so of you winning the bet, we have to multiply all these fractions. Don't worry, I've done it for you. So the probability of you winning the bet is pretty much 0%. Well, that was a bit too extreme, so let's ask another question. What is the smallest number of people I would have to gather to make the odds in my favor? So what's the smallest group of people that will still make probability of you winning the bet smaller than 50%? In fact, in a group of only 23 people, yes, in a group of only 23 people, the probability that someone is sharing birthday is slightly over 50%. And in fact, you can use this knowledge next time you watch a football game. So you can bet your mates that on the pitch you will find a pair of birthday twins. You aren't guaranteed to win, but maybe your chances are slightly higher than betting on the victory of your team. You figured. It's exactly 23 men on the pitch, 2 teams of 11 and 1 referee. Birthday problem is just a fun fact, but similar calculations are the basis of many sciences using probability and statistics. So pretty much every science you can think of. For example, I guess most of you checked the weather forecast today before leaving your house. And did your favorite app tell you if it's going to rain in London today? It shouldn't have. Instead of a definite it will or it won't rain, you should have seen a probability of precipitation, so how likely it is that any rain will fall in London today. And to get this number, we basically do a more complicated version of the birthday problem. Probabilities are everywhere. I don't know about you, but maths makes me hungry. And it's a maths party, so what's the classic party food? Pizza. If you know how to eat pizza properly, there are 2 possibilities. You either excel in maths or you're Italian. Otherwise, you're way too familiar with this problem. Pizzas are delivered, you're ready to bite into your delicious slice, and this happens again. The slice flops over and all the toppings are on your favorite shirt. Is it because you're sloppy? No. It's because you haven't paid enough attention to mathematics. Let's go back to the 19th century to meet an ingenious mathematician, Mr. Gauss. One of his hobbies was studying curved surfaces. And in fact, we can quantify how much a surface is curved using a number called a curvature. Example, a piece of paper. It's completely flat, its curvature is 0. But when we roll it into a cylinder, see what happens. If you were a tiny little creature, you could trace a circle, so a curved path, or follow up a straight path, or something in between, like a helix. And this made Gauss very, very unhappy, because one object shouldn't have many different curvatures, right? So he defined a Gaussian curvature, which intuitively is a product, so a multiplication of the smallest and the biggest curvatures at a given point. Don't panic. Details don't matter here. What matters is a remarkable theorem by Gauss. Literally remarkable, as we translate the original Latin name Theorema egregium. This theorem tells us that Gaussian curvature doesn't change even if we bend the surface, as long as we don't shrink, stretch, or tear it. Why am I talking about geometry while your pizza is getting cold? Because the remarkable theorem is really remarkable. It provides us with a pizza eating strategy. So, you have a slice lying flat on your plate, so the curvatures in all directions are 0. Again, I won't define them precisely, but come on, what else could they be if the pizza slice is completely flat? Now, the trick is to bend the slice in half and see what happens. So in one direction, it's definitely curved. Its curvature, in fact, is negative. But remember, the Gaussian curvature stays the same, stays 0. So if we multiply the negative number by the curvature in the direction pointing towards your mouth, we still need to get 0. Which means that in this direction, the curvature will still be 0. The pizza slice will stay flat, it won't flop over. Thank you, Gauss, for saving our shirts. Theorema egregium has many applications, some of them a bit more serious than eating pizza. Although, what can be more serious than eating pizza when you think about it? For example, all maps are distorted in some way, because we are trying to translate something from a globe with positive curvature on a flat map with curvature 0. And because of Gauss, we know it's impossible. It's like trying to get a peel of an orange and put it flat on a plate without cutting it. That's why cartography is such a tricky field, and why some of us think that Greenland is the same size as Africa, even though it's 14 times smaller. It's because we are used to the so-called Mercator projection that saves the shapes of land masses but distorts their sizes. And again, because of Gauss, we know we can't keep both. Be it a party or earth sciences, we can't avoid maths. It is literally everywhere, no matter if we want it or not. In everyday life, we encounter its different areas. Everything we do involves mathematics. Big theorems aren't just for big scientists to solve big problems. They can help you comb your hair, impress birthday guests, or eat pizza properly. But while you are getting rid of tufts on your head, we can study wind behavior. While you are taking bets on birthday party, we calculate the probability of precipitation. While you're enjoying your pizza, cartographers are figuring out new ways of making more adequate maps. Maths helps us solve problems. Global, like climate change or epidemics, but also very personal ones, such as how to cut a cake properly, or how many people should you date before you get married. But maybe even more importantly, maths is fun. Thank you.